Okay, so now we're going to introduce the matrix equation of a linear system. And what I want to do is I want to do it by example. So this is kind of informal, but I think this is enough to get the idea of how this works. So here we've got a linear system. We've got two equations and three variables. Right? So let's, rather than jumping into writing down the augmented matrix and solving this, we're going to do something else. Let me start by rephrasing this as an equation involving two vectors. So let's do the following. So I'm going to write this as x1 plus 5x2 minus 2x3. So what am I doing? I'm building a two-dimensional vector where the coordinates are going to be the left-hand sides of each of these equations. So I've got 2x1 plus 6x3 as my second coordinate. So now I've got a vector. Okay, and I've just taken the left-hand side here and the left-hand side here, and I put them together into this vector. Now I'm going to do the same thing with the right-hand side. I'm just rewriting this equation, or pardon me, I'm rewriting this linear system as a vector equation. And now I can split the left-hand side up into the sum of three vectors. So I'm writing this as x1, 2x1, that's the first vector. The second vector, I'm going to go 5x2, 0 for the second coordinate. And then for the third vector, I'm going to go negative 2x3, 6x3 for my second coordinate. And then the right-hand side won't change. Okay, and just pause for a moment and make sure that you believe this works. Right? If I take this vector and I add it to this vector and then I add the result to this vector, I really am going to get this vector. Because if I add up all the first coordinates here, you're going to get exactly the first coordinate of this vector. And if I add up all the second coordinates, I'm going to get exactly the second coordinate of the left-hand side here. So that really truly is a valid step. Now, why did I split it up like that? I wanted to get each of the variables by themselves. So x1 is only showing up in this vector, and x2 only shows up in this vector, and x3, why is that an x6? That should be an x3. x3 only shows up in this vector. So because I did that, now I can pull them out as scalar multiples. So I can write this as x1 times 1, 2 plus x2 times 5, 0 plus x3 times negative 2, 6. And then the right-hand side again doesn't change. Notice what happened here. We've translated this linear system into a vector equation that, look, what does this look like? This is essentially saying, okay, the constant column, right, the vector that consists of just all the constants from each of constant terms from each of these linear equations, this has been written as a linear equation of three vectors, and the weights x1, x2, and x3 are precisely the variables from the original linear system. That's kind of an interesting thing. It's an interesting way to change perspectives. And actually, if you now even go a step further, this is the definition of a very specific product of a matrix and we can call it a variable vector. This is the left-hand side of this equation is actually the product of this 2 by 3 matrix. That 2 by 3 matrix multiplied by this 3 by 1 matrix. I like to call these variable vectors because it's a vector where each of the coordinates are actually variables from a linear system, and then that equals the constant column on the right-hand side. Okay, so, and you can notice, hey, this is nothing but the coefficient matrix of this linear system, and this is the constant column of this linear system. And in fact, if I took the coefficient matrix and the constant column and I squished them together, guess what I'd get? I'd get the augmented matrix of this linear system. Let's actually write some of this down, jot some of this terminology down. So I'm going to label this as star so I don't have to rewrite it. This down here, this is called the matrix equation of star. In other words, it's the matrix equation of the linear system that we started with. Okay, that's an important term. So let's underline that. Okay, and this gives you three different points of view for a linear system. One of them is just looking at the linear system exactly how it's written. Another way we can look at linear systems, and this is what we've done in the past, is we can write down their augmented matrices. So I'll just do that here. And you notice these are exactly the entries that are showing up in the coefficient matrix and the constant column. That's what I meant by saying if you squish them together, you're going to get the augmented matrix. And now you have another way to look at it. You can, I'm just going to take a copy of this and put it up here. You have the matrix equation, and the matrix equation is equivalent to the augmented matrix, but it's also equivalent to the linear system. Solving this linear system is exactly the same as solving this matrix equation, and the augmented matrix is the tool that you would use to do it. So let's write another comment in here. These are all equivalent. Okay, so that's really useful to have the ability to shift points of view there. Okay, let's jump down to this example here. Solve each matrix equation. Notice that this matrix equation is exactly what we ended up with in the previous example. So if you're asked to solve this matrix equation, what you really want to do is you want to solve the underlying linear system. You want to solve this linear system. So how are you going to do it? Well, you're going to set up this augmented matrix. In fact, since we've already written it down, why don't we copy this and use it as a starting point down here. And we're just going to need to row reduce that system. Row reduce that augmented matrix, and we can get the solution that way. Okay, so let's go ahead and do that. So let's get this into reduced row echelon form. I'll take row 2 and I'll subtract row 1 twice. So what's that going to do? We'll have 1, 5, negative 2, 3 for the first row. Second row, we're going to have 0, negative 10, positive 10, negative 10. Then we will, I don't like these 10s, I want to reduce them. Since they're all a multiple of 10, I'm going to take row 2 and replace it with negative 1 over 10 times row 2, and that'll have the effect of simplifying that second row quite a bit. So we'll have 0, 1, negative 1, positive 1, like that. And then lastly, I'm going to take row 2, so take row 1 and subtract row 2, but I'll do it 5 times, just to get rid of this 5. Okay, so what's going to happen? We'll have second row won't change, 0, 1, negative 1, 1. What happens to the first row? We're going to have 1, 0, and so we're going to, here, be careful, we're subtracting negative 1 5 times, so that's like adding 5. So we're going to have positive 3 here, and then here we're subtracting 1 from 3 5 times, we're going to have negative 2. Okay, so now we can pick out the general solution here. Remember what your variables are. They're x1, x2, and x3. That's what these 3 columns correspond to, x1, x2, and x3. So starting from the right, x3, there's no parameter, or pardon me, there's no leading 1 there. So x3 is going to be assigned a parameter. Let's use the letter S. Then I'm going to move 1 column over to the left, and I'm going to say, okay, this column does contain a leading 1. It does have a pivot position in that column. It is a pivot column. So, okay, write out the equation that corresponds to the pivot row. That's going to be x2 minus x3 is equal to 1. So now solve for x2. So we'll have 1 plus x3. Or, in other words, since x3 was a free variable, we can plug in its parameter, which gives us 1 plus s. And then lastly, finally look at the first column. And again, that is a pivot column, so we're not going to assign a parameter. We're going to instead look at the corresponding pivot row and write out the equation that corresponds to that row. So we'll have x1 plus 3x3 is equal to negative 2. Now we'll isolate x1, and you get negative 2 minus 3x3. Or plug in the parameter, and you're going to get negative 2 minus 3s. Okay, so now we can write down the general solution here, or the solution. It's also called the general solution. Whenever you have a solution that involves parameters, if you refer to it as the general solution, you're really just emphasizing the fact that there's many solutions. Okay, so what do we have here? We've got x1 is negative 2 minus 3s, x2 was 1 plus s, and x3 was s. and this is for arbitrary real numbers S. That's the general solution. Okay, so really this just amounted to solving a linear system. Most of the work in this example, this could have been from section 1.2, right? That's where we learned how to solve systems of this form. But the purpose of this example is if you're solving a matrix equation such as this one, it's the same as just simply solving the underlying linear system. That's one of the main points of this example. And the other main point, well, it'll come up after we do part B. And hey, this was only part A, so why don't I label that? Okay, and part B we'll do on the next page.